Hello everyone and welcome to lecture today. So today what I want to start doing is getting into actually doing some calculus with parametric curves. So we've seen a number of really good examples of general parametric curves and polar curves, and we want to see how we can use calculus to essentially study the properties of these curves and to go through and actually compute some actual, geometrical values associated with these curves. And it turns out that there's a lot of very rich mathematics going on here that we can directly go through and use calculus to solve problems. So for the following, let's assume that we have a parametric curve where the x-coordinate is a function of t, and specifically we'll say that it's some function f of t, and y is some function g of t for t in some interval I from a to b, where a is the beginning point of this interval, b is the end point of the interval. So it's some curve that's parameterized by this parameter t. The first main result that we have is if these two functions f and g are differentiable, we can directly go through and actually use what we know about the chain rule to figure out what the derivative of y with respect to x is in terms of the parameterization. Specifically, we recall that from the chain rule, the derivative of y with respect to t is going to be the same thing as the derivative of y with respect to x times the derivative of x with respect to t. This is coming directly from the chain rule. And so long as dx dt is not equal to 0, then we have that dy dx must be equal to dy dt over dx dt. Or to put it more exact, in terms of the parameterization, dy dt is going to be g prime of t over dx dt, which is going to be f prime of t. And you can shorten this to m of t if that kind of helps you think of this, because we know that in the y-x plane, dy dx, the derivative of y with respect to x, is going to be the same thing as a slope of a tangent line to the curve. Now, this is a very, very powerful result, because essentially this allows us to figure out what the slope is in the y-x plane of any parametric curve. It can be very complicated. It doesn't necessarily have to be a function. So the first example that I'll consider in using this formula is going to be a general ellipse. And an ellipse has a similar equation to a circle. It's x over a squared plus y over b squared is equal to 1. you can see how it relates to a circle. If A is equal to B is equal to R, then this equation right here reduces to x squared plus y squared over r squared is equal to 1, or x squared plus y squared is equal to r squared, which is our standard equation of a circle from trigonometry. So this is the more general equation of an ellipse, where we typically call A and B the semi-major and semi-minor axes, depending on whether or not A or B is larger. So we saw how to parameterize a circle in the previous lecture. Parameterizing an ellipse is done in a very similar manner. If we take x equal to A times cosine of t, and y equal to b times sine of t, it's, I think, very clear to see that these two parameterizations satisfy this equation in terms of this Cartesian equation in terms of x and y. If you take a times cosine of t and you plug into this equation, you're going to be left with cosine squared. And if you take b times sine of t and plug into this equation right here, you're going to be left with sine squared. And we know that cosine squared plus sine squared is equal to 1. So this is the correct parameterization of an ellipse. The segment of the ellipse that we're looking at is determined by the interval with respect to t that we look at. So the full ellipse will be from 0 to 2 pi, but a segment of the ellipse will correspond to t from 0 to some angle, and you can get any segment of the ellipse that you want. So the idea here is that this is our f of t, this is our g of t, and to apply the previous formula, then we then have that dy dx is equal to g prime of t over f prime of t, or the derivative of g is going to be the derivative of b sine theta, which is b cosine of t, over the derivative of cosine, which is negative a sine of t. So if you take the derivative of f in the denominator here, so this is negative b over a cosine of t over sine of t. And what we've just done is solve for an equation that on the ellipse gives us at every point the slope dy dx of the tangent line to the curve. And you could even go through and plug in any different value of t that you want on this interval to get the value of this slope. But in general, the tangent line, right, for a given, we'll say t naught, or dy dx at some value t naught is going to be m naught, or this m with t naught plugged into it. So the tangent line, the equation of the tangent line for any value t naught on the ellipse is going to be, and really this equation works for any curve, m naught times x minus x naught plus y naught, where m naught is the slope from this formula. For a different parametric curve, you're going to have a different formula, but for this parametric curve, we're going to have negative b over a cosine of t over sine of t, and x naught and y naught here are just the points on the ellipse. So x naught is f of t naught, and y naught is g of t naught. To get a nice visualization of this, I made some GeoGebra code to plot this tangent line. It's exactly y equals m naught times x minus x naught plus y naught. And you can even change the point t naught, or the point x naught, y naught, by changing the value t naught that you're evaluating the point at. So here this gray point is x naught, y naught. And this green line is the tangent line of this curve. And hopefully you can see that what we've done here is a little bit more general than just what you may have learned in your Calculus 1 class, because now we can deal with curves that aren't typically functions. Y is a function of x. We can deal with more complicated looking curves using this idea of parametric curves. Right? Just because the ellipse isn't a function of x, y is a function of x, we can still deal with it in terms of using the tangent line approximation on the curve. So I want to do one more example just to make sure that we're understanding everything. And for this, I'll use the exponential spiral that I discussed the last lecture. Recall that this is x is equal to the function f of t, e to the omega t times cosine of t, and y is equal to the function e to the omega t times sine of t. So this function is our g of t, and this function is our f of t. And the nice formula that I wrote down before, dy dx will be equal to g prime of t over f prime of t and it helps to have these values readily calculated. So let's go through. Dx dt is going to be f prime of t, which from the product rule will be omega e to the omega t times cosine of t plus e to the omega t times the derivative of cosine, which is negative sine. So f prime of t will be equal to e to the omega t times omega cosine of t minus sine of t, and dy dt, or g prime of t, will be omega e to the omega t times sine of t plus e to the omega t times cosine of t, and the product rule applied to this product. So g prime of t will be e to the omega t times omega sine of t plus cosine of t. And we can directly plug each one of these expressions into our formula to get the following expression that gives us dy dx at any point on the curve. We also get a really nice cancellation right here. So this right here is exactly our m of t, or the slope of the tangent line on this exponential spiral for any value of t in the range of parameters, or the range of the parameter space. Remember, t will always be going from some lower bound to some upper bound. if we look to our visualization GeoGebra applet right here, this is a plot of this curve from, I think the initial t value I chose was 0, and the final t value I chose was 10 pi. So this is when t equals 0, this is when t equals 10 pi. And this is, again, the tangent line plotted at some point t naught. In this case, the point is around 0.53 for the value of t. In the slope of this tangent line is exactly m naught, which is g prime at the point over f prime. So here it's about negative 1.372, but just like before, if we move the point around the curve, we change the point where the curve is, this value of the slope is changing. This becomes negative 0.321, and as t gets larger and larger, we get to a point where we're like right here, where it's almost 0, and then the slope becomes positive. And you can kind of watch this go around. And what's special here is that this curve is much more general than any function you might consider in Calculus 1, because this curve is not, you cannot express y as a function of x on this curve. It does not pass the vertical line test. Nevertheless, using parametric curves, it's possible to very nicely define the points on this curve and study the properties of this curve using calculus. So the big point of this formula is essentially figuring out the derivative of y with respect to x using the parameterization as a tool for us. So just through using the parametric relationships between x as a function of t and y as a function of t. And this is the power of this formula right here and why it's very helpful. We have, in addition to this, we can go through and develop generalizations to this formula for any number of the derivatives of the function y with respect to x that we want. For instance, I'll do the second derivative here. This requires a little bit more of an assumption on the functions f and g. If f and g are twice differentiable, so the derivatives of f and g both exist, and they define y as a twice differentiable function of x at any point where dx dt is non-zero, and y prime, we'll say, is dy dx. Then the second derivative of y with respect to x, which is the same thing as the x derivative of the y derivative with respect to x. This is the same thing as y prime, or dy dx, and this quantity is going to be equal to the derivative of y prime with respect to t over the derivative of x with respect to t. So this formula very nicely generalizes. The whole reason here is because it's based on the chain rule. So the idea here is that for any function u, du dt is going to be the same thing as du dx times dx dt. So du dx will be equal to du dt over dx dt. I want you to be really careful with this notation here. This is not saying that the dt's cancel out. It's saying that the derivative of u with respect to t will, or derivative of u with respect to x will be equal to the derivative of u with respect to t divided by the derivative of x with respect to t. This is just the chain rule. So to get this relationship, essentially what we're doing is just plugging in the relationship from the previous theorem dy dx. Right? Dy dx is the same thing as this u that we're kind of inserting into this equation. And so this is going to be the same thing as du dt over dx dt. But this is a super useful formula. Not only that, but we can use what we know about the quotient rule to get a very nice expression for this, which is a little bit longer than this expression. So I prefer this expression right here, but in terms of just f and g. So we know that dy prime dt is the same thing as the t derivative of y prime. Y prime is g prime over f prime. And this is going to be divided by dx dt, which is f prime of t. So from the quotient rule, this is the same thing as the derivative of g prime, which is g prime prime, times f prime, minus g prime, times the derivative of f prime, which is f prime prime, over f prime of t squared. This is the quotient rule applied to the numerator in this expression. And this is divided by f prime of t. So this is the same thing then as g prime prime of t times f prime of t minus g prime times f prime prime of t divided by f prime of t cubed. Or put into a slightly simplified formula, g prime prime is going to be, say, x, or g prime prime is going to be y dot dot times x dot minus y dot times x dot dot divided by x dot cubed, where this dot notation I'm using just to denote the t derivative of the quantity. So it's definitely not expected that the second derivative is going to be at this relationship to the second derivative in the first derivative of the parametric equations x and y of t. But this is pretty neat that this works out like this. So these are some of the neat things that we can do with the derivative of the components in a given parametric curve. Using many of the rules from Calculus 1, we can kind of go through and very nicely get some relationships that all parametric curves, as long as they're smooth enough, so nice enough in some sense mathematically, what they have to obey. We can also do the same thing with many concepts from Calculus 2, or integration. And one of the biggest concepts to kind of think about is how to generalize and use the definite integral. This is going to lead into, right now, what's called the arc length of a curve. So suppose that we have some parametric curve, x equals f of t, y equals g of t, for the parameter t between a and b. The arc length of the curve is the actual physical length, geometrically, from the beginning point of the curve all the way to the end point of the curve. So if you were to say take a measuring tape and kind of stretch it along this curve and figure out what the length of that measuring tape is, that's exactly what the arc length is from A to B. In order to figure out a general formula for this in terms of f and g, we're going to need to use integration and clearly explain how to get that formula. So the first thing that we do is form a partitioning of our domain, where the initial point of the partition, t0, is equal to a. The final point of our partition is tn, which is equal to b. And the partition then will contain n segments going from t0 to tn. So we say t1, t2, t3, and so on and so forth, all the way up to tn-1 up to b, where each one of these values satisfies t0 is less than t1, is less than t2, is less than t3, all the way up to the end point. And this process will be familiar to you if you've taken a Calculus 2 course and studied Riemann sums for the definite integral. Basically, what we need to do is figure out what the correct Riemann sum is that will give us the length, or the arc length, of this curve in the limit as this partition gets finer and finer and finer. This is a picture with seven intervals in our partition, and you can clearly see here that the sum of the length of each one of these line segments is going to be approximately equal to the actual length of the curve. And as we increase the number of points in the partition, or the number of subintervals, we do expect this approximation to get better and better and better and better. The sum of each one of these lengths is going to better and better and better approximate the total length of the curve. So what we need to do is investigate the length associated with a given one of these segments. And so what I did here is just kind of zoom in on any one of these segments. You can zoom in on any one you want. For any number of terms in the partition, the segment is always going to be a straight line that's of a length, we'll call it delta sk for the kth term in the partition. And we know that delta sk squared will be equal to delta xk squared plus delta yk squared from the Pythagorean theorem on this right triangle. Okay, and this is true for any one of these segments. So it's true in general for any k, for any number of partitions, or for any number of segments in our partition. This formula right here is going to be the key for us, because we know that delta sk then will be the square root of delta xk squared plus delta yk squared. And for a given partition, then the length of the curve, the arc length of the curve from A to B, will be the summation from k equals 1 to n of delta sk. So this summation is the approximation to the actual arc length of the curve. Now, it's important to investigate exactly how delta xk and delta yk are related to the functions of the parametric curve. And we know that delta xk is going to be f of tk minus f of tk minus 1, and delta yk will be g of tk minus g of tk minus 1. And there's a really nice theorem that you hopefully learned in your Calculus 1 class called the mean value theorem. And both of these equations that I'm going to write down are directly due to the mean value theorem. It says that if, as long as f and g are continuously differentiable on any interval, the difference at the endpoints of the interval of the function is going to be equal to the derivative of the function at some point inside the interval. So I'll call this point ck for f, times the distance of the total interval. So tk minus 1, or f prime of ck times delta tk. We have this exact same result for g on the interval from tk minus 1 to tk. So g of tk minus g of tk minus 1 will be equal to g prime of some dk times tk minus tk minus 1, or g prime of tk. And this is really the key to showing the limit of this as n goes to infinity. We know that the approximate length is going to be the sum from k equals 1 to n of delta sk, or the sum from k equals 1 to n of the square root of delta xk squared plus delta yk squared and from the mean value theorem we have that this is going to be the same thing as f prime of ck delta tk squared plus g prime of tk delta tk. squared. Where we can factor out the delta tk squared to get that Sn is going to be equal to the summation from k equals 1 to n, the square root of f prime of ck squared plus g prime of dk squared times delta tk. And although this limit is not a Riemann sum specifically, because the sample point here, you have two different sample points, ck and dk, nevertheless it can be shown directly that as the partition gets finer and finer and finer and finer, so you include more and more and more points in your partition, so as n goes to infinity, the actual arc length from A to B is in fact equal to the definite integral from A to B of the square root of f prime of t squared plus g prime of t squared with respect to t. The main conditions that we need to apply this theorem is that f prime, the derivative of f, and g prime must be continuous and not both simultaneously 0 on the interval from A to B. But this is how we define the arc length of a curve from 2 points on the curve. Let's see an example of this. I'm just going to use the circle of radius 2. So x is going to be 2 cosine of t. Y is going to be 2 sine of t. And we'll do it from 0, t on the interval from 0 to 5 pi over 4. So visually, this is this curve right here. If you get the length of this curve right here, our x is the f of t, and our g of t is 2 sine of t for this example. So dx dt will be f prime of t, which is going to be negative 2 sine of t. dy dt is going to be g prime of t, which is going to be 2 cosine of t. And so the arc length of a circle from 0 to 5 pi over 4 is going to be the integral from 0 to 5 pi over 4 of the square root of f prime squared, which is going to be negative 2 times sine of t squared plus 2 times cosine of t squared dt. And this is going to simplify then to be from 0 to 5 pi over 4. Sine squared plus cosine squared is 1. Negative 2 squared is 4, and 2 squared is 4. So this is the same thing as square root of 4 times the square root of sine squared plus cosine squared, which is 1. Or 2 times the integral from 0 to 5 pi over 4, 1 dt, which is just equal to 2 times 5 pi over 4, or 5 pi over 2. So what I want to do is give you a visualization of this and what exactly this Riemann sum process does, as well as verify this formula just for this example. So the idea here is that in the background I see there's a circle of radius 2 that I plotted, and we're specifically interested in the arc length from t equals 0 from this point all the way to this point right here, which is when t equals 5 pi over 4. Remember, the Riemann sum process just takes the length of each one of the segments in the Riemann sum, or each one of the segments of the partition, and sums up those two lengths. So that's what this approximate length is right here. It just adds up all of the distances of the partition. So geometrically, you can see clearly that if I add a point to the partition, this listing, right, or I guess our delta sk for each one of these, is delta s1, delta s2, delta s3, is getting much nicer and more approximate to the actual length of the curve, and even more so if I had 4, 5, 6, right, or 7 total points to, or 7 total segments to the partition. So that n here is the number of segments of the partition. And what I did was I actually, because we calculated the exact value, 5 pi over 2, I put in an error value, which is the approximate length minus the exact length, to show you really how well this is doing as we go from 2 points in the partition up to 50 points in the partition. You see that the error is very quickly decreasing, right, when we get to a partition with 50 segments in it, the error decreases down to 0.002. So this Riemann sum procedure really is giving us the true value of length in the limit as n goes to infinity, which is why this integral formula holds. In fact, for the circle and many other curves, we can go through and do this explicitly for any angle theta that we want. So for the circle, the arc length as a function of theta is going to be the integral from 0 to theta of the general expression f prime of t squared plus g prime of t squared dt. And this is if f of t for a general circle is r times cosine theta, and g of t is r times sine of theta, and we go through and do the same really calculation that we did before, so I'm not going to redo it. This right here will simplify to being equal to r times 1, which when we do this integral, because the r is a constant, it comes out, we get that the arc length as a function of theta for the circle is r times theta. So s equals r times theta for the circle. So if you have a segment on the circle that you're looking for the arc length of, it directly comes as the radius of the circle multiplied by theta. This is a very neat formula, and a very, very useful formula in many contexts. I want to do one more example to make sure that everything's crystal clear. And for this next example, I'm going to consider again the exponential spiral, which is given by e to the omega t times cosine of t It's the x-coordinate, and the y-coordinate is e to the omega t times sine of t. And for definiteness, we'll consider this in the same interval from before for t from 0 to 10 pi. And recall from before that we computed the derivatives of each of these curves to be f prime is this and g prime is this earlier in the lecture. So what I want to do first is simplify f prime of t squared plus g prime of t squared before we go about doing the integral. We know we're going to need this for a function in the integral for the arc length. It's going to be much easier if we kind of simplify this before going through and actually doing the integral itself. So it's going to be this quantity squared under a square root plus this quantity squared under the square root. I need to make my square root a little bit bigger here. So this is the thing that we have to integrate, which admittedly is a little bit complicated. And for other problems, this does become quite the complication. There's certain arc-length integrals that are actually not integrable in closed form. Specifically, if you go to do the arc length of a general ellipse, unlike a circle, you will get that you will not be able to find the closed form solution for the antiderivative of that function. Luckily, this is going to simplify very nicely. So it's f prime squared plus g prime squared. And this will be equal to e to the 2 times omega t times omega squared cosine squared plus sine squared. Both of these are of t. I'm just foiling out this term right here. So it's this squared plus this squared minus 2 times omega times cosine of t times sine of t. In this term, we also get e to the 2 omega t, so I can just factor that out from the entire thing. This will be plus omega squared sine squared of t plus cosine squared of t plus 2 times omega times sine of t times cosine of t. And it's the square root of this entire expression. Again, it looks even more complicated as we foiled out this term and this term, but you'll notice that we have negative 2 times omega times cosine times sine, which cancels with positive 2 times omega times sine times cosine when they're added together. And we also have that this is going to be then the square root of e to the 2 times omega times t times omega squared cosine squared t plus sine squared t plus sine squared plus cosine squared. Both of which are 1. And the square root of e to the 2 times omega times t is the same thing as e to the omega times t. So really, we actually have a very nice simplification for f prime of t squared plus g prime of t squared under the square root. And so the arc length from 0 to 10 pi is going to be the integral from 0 to 10 pi of this function e to the omega t times the square root of 1 plus omega squared dt. And this is going to be equal to the square root of 1 plus omega squared, is this constant with respect to t, times the antiderivative of e to the omega t, which is e to the omega t over omega, evaluated from 10 pi to 0. So the exact value of the arc length of this curve is going to be 1 plus omega squared over omega times e to the 10 pi omega minus e to the 0, which is 1. And this is the exact value of the arc length of this curve from 0 to 10 pi in terms of any value omega. And to really show this, I want to go through and really demonstrate this, that this Riemann sum process is working and at least geometrically giving us the this exact value. So if I increase the number of points in my partition on this curve from n equals 2 to n equals 100, we see that initially it's not a very good approximation, but as we get more and more and more points, we're achieving a very, very nice approximation to the total length of the curve. Specifically, this is the curve with omega equal to negative 0.1. So if we look at the approximate length, which is the sum of all these lengths, in the absolute value of this minus the actual value, square root of 1 plus 0.1 squared over negative 0.1 times e to the negative 0.1 times 10 pi minus 1, we're getting an error of 0.03, which is not super nice, but it's definitely converging. If we were to add more points to this, we get a much better approximation to the total length. But that will conclude today's lecture. Thank you very much for listening. I hope you learned something and had a great day.